This lesson includes a brief review of applications using steel fiber reinforced concrete during its 50 years of experience. The approximate annual consumption of structural fibers for concrete in Spain was around 38,000 tons in 2007. It was close to an equal distribution between mining and tunneling, with projected concrete precast elements or segments, and pavements, industrial, ports, airport, roads. Common applications of steel fiber reinforced concrete comprises also overlays in the bridge decks, thin shell elements, seismic and explosion resisting structures, and many others, being a versatile and practical technology with a wide range of uses. An example shown in the top left of this slide is El Navío Quay in the Algeciras port. It is a pavement for containers constructed in two phases. In 1986, a 25 cm thick pavement was built, and the second phase in 1994 included a 30 cm thick pavement with a total of 35 kilograms meter cube of steel fibers. Another construction of this kind in the center top of the slide is the Cerro Muriano military pavement for tanks of up to 60 tons, which implied important demands due to the tanks' movements. Productivity improvements and the reduction of thicknesses and weights have made of steel fiber reinforced concrete an attractive solution for precast elements as those shown in this slide. Replacement for conventional steel mesh in industrial ground floor slabs is the most spread use, being nearly 65% of the fiber produced worldwide, used in floors, road pavements, or other types of slabs on ground. By adding steel or synthetic structural fibers, research has shown to be possible to reduce the minimum required ground-supported slab thickness. The two main requirements for slab designing and shrinkage control and post-cracking strength are post-cracking strength, in which steel fibers are very adequate. As a tunneling construction example, this slide shows a view of the segments for the Barcelona subway Line 9. Projected concrete in tunneling, as well as the tunnel precast fiber reinforced concrete segments for tunnel boring machine, have been extensively used as reported in bibliography. Their potential for production, improved handling and robustness, and long-term durability benefits are probably the main reasons. Structural situations should include transitional load cases as the molding, storage, transportation and handling, as well as construction load cases of TBM thrust jack forces as grouting pressure. In structures with relatively low reliability level, such as slabs on grade, foundations or walls, total substitutions of steel bars is possible, and in some other load-carrying structures, reinforced concrete and fiber reinforced concrete can be profitable to be combined. However, concerning structural steel fiber reinforced concrete, it should be noted that the possibility of total substitutions of the continuous steel bar reinforcement in isostatic structures and their uniaxial bending is still pending and remarkably complex. Nevertheless, the addition of fibers encompasses successfully the substitution of steel bars in elements with significantly variable stress distributions or pieces working in 2 or 3 dimensions. That would be the case of the wall of the promenade Paseo Marítimo in Benidorm, shown in the right side of the slide. Other more specific applications of steel fiber reinforced concrete are those in which, due to the structural configuration of loads, only compressive stresses are expected, such as double curvature cells. The composite material resists the minor bending that occurs during the life of a real structure, as in the thin shell of the submarine restaurant in Parque Oceanográfico site in Valencia, and shown in the slide being one of the most representative constructions using fiber reinforced concrete. Maybe the most striking examples of the use of steel fiber reinforced concrete are footbridges. More than 20 bridges, including motorway bridges, have been constructed using ultra-high performance fiber reinforced concrete in Japan. The Sakata Mirai footbridge, shown in the slide, was the first one, constructed in 2002, and it was located in a saline environment not being detected deterioration after 10 years of construction. In the top image, another example of the use of the so-called ultra-high performance fiber-reinforced concrete, combining several advanced technologies of concrete, such as fiber-reinforced concrete, high-strength concrete, and self-compacting concrete, have shown to be possible and economical in some applications, as in the footbridge over the Ovejas ravine in Alicante, Spain. The construction industry and precast companies are exploring some other special applications of fiber-reinforced concrete with new requirements. That is the case, for example, of the FRC wind towers. The trend of such towers is to require taller towers up to 140 meters. Concrete towers have higher self-frequency than similar steel towers, but also around 3 times more mass and 5 times more damping, and therefore it reduces dynamic effects. Precast fiber-reinforced concrete is especially suitable for wind towers due to its fast execution, extended linear response, and improved fatigue performance, and therefore cost efficiency. Summarizing, the graph in the slide shows the overall consumption of steel fibers in each type of application in Europe. As can be noticed, new structural applications are being used nowadays, in addition to the most traditional ones of pavements and tunneling. Thank you for your attention.